Good morning, ladies and gentlemen, boys and girls. Coming back at you with part B of the 2018 AP Calculus AB free response. Part B meaning no calculator. So put those calculators away. Next 4 questions, 3, 4, 5, and 6 are to be done without a graphing utility. Okay, so let's jump in with number 3. The graph of the continuous function g, the derivative of the function f, is shown above. We'll do that again. The graph of the continuous function g, so this is g, the derivative of the function f is shown above. So that, for whatever reason, took me forever to figure out what they were saying. G, but it's simple. G is the derivative of f. So g equals f prime. Okay? The function g is piecewise linear between -5 and 3. And g of x equals this quadratic for between 3 and 6. Okay, so in other words, we can assume where it looks linear that it is indeed linear, and they give us the function for this guy here. Okay, so let's get to it. First question. If f of 1 equals 3, what is the value of f of -5? So again, they're asking us about function values on f. But what we have is g. So how in the world are we going to figure that out? Well, this is really going to display our understanding of exactly what the derivative of a function is tracking and how that relates to the function values of the derivative itself. So we need to come up with some relationship between the function value at 1 and the function value at 5. Okay? So I'm going to start out kind of very generic and basic. I'm kind of making this up as I go, so if it doesn't totally flow, forgive me. But in general, for any function, we can have a starting value plus some change and that's going to get us to our ending value. Okay, and I'm being purposefully a little opaque here and obtuse, but starting value will have some change happen on that function and we get to the ending value. Well, we have specific things we can refer to instead of just starting value, some change, and ending value. Looking at our graph, if we were to start at our function value at 5, wherever that is, because again, this is not our function f, this is our function g, its derivative. Wherever we start at f, or at -5, the function is going to do whatever it does, so some change, and then we're going to end up at the function value of the ending value, which is f of 1. Okay? So we know where we want to start. F of -5 is our starting value, plus some change, and then we're going to want to get to f of 1. And we know what f of 1 is. So f of -5 is an unknown. So the question is, what the heck is this some change? Well, it's exactly the accumulated change between -5 and 1. Accumulated change? Oh, integral. Okay? So this is the sum change is going to be the integral on the derivative of our function here on some starting value, which is -5 to 1. Okay? This tracks the change, this accumulates the change, and if we start here, these are all the changes, we'll end up at the function value. Okay? So we can be a little more precise when we start our actual problem. And so part A, we're going to have that f of -5 plus the integral from -5 to 1. Well, f prime we know is g of x is going to be equal to f of 1, which is a value that we know. we're trying to find f of 5. And so we can rearrange this and arrive at the fact that that function value of f is going to be equal to f of 1 minus the integral from negative 5 to 1 gx. Oh, we should have dx's in here. My bad. dx. Okay. If we look at our graph of g from negative 5 to 1, these are geometric problems all day. Okay. So yeah, let's just go through and figure out what each of these parts of our integral are going to be. Use a pencil here just in case I make a mistake, but this one looks like negative 9. This guy right here is a triangle, base 1, height 3. Let's call that 3/2. And then this guy, triangle, base 1, height 2. We'll call that 1. Okay, so our integral, and here we can plug in for f1 as well. We know f1 is 3 because they told us that, minus this integral is going to be negative 9 plus negative 3/2 plus 1. Okay, I would box this up and run for your life, because the only bad things are going to happen with fractions. Of course, we will, just for the sake of curiosity, simplify this, but this is an acceptable answer. Okay, but if we wanted to get the exact, we could have 3 minus, turning these into halves, we get negative 18/2 plus negative 3/2 is like negative 21/2 plus 2/2 is negative 19/2. Which looks a lot like 3 is really 6/2, and that turns into an addition, so we get 25/2. 25/2. Okay, but again, let's box this up so we don't make the stupid mistakes. We do not have our calculators. So in terms of points, you got 1 point. This was a 2-pointer. You got 1 point for setting up the proper integral, this sum change thing, and then you got 1 point for the answer. 2 points. Okay, so that was a tricky little question. You would definitely have to be able to show that you understand what the derivative of a function is doing. It's tracking that change, and what happens when we accumulate that change. Well, it lets us go between ending and starting values. Okay, so part B, moving right along, asks us to evaluate the definite integral between 1 and 6. Between 1 and 6. So just from here to here. Okay, so let's just like kind of game plan this before we actually do it. Between 1 and 6, we want all of this area. Okay. Well, to me, I'm thinking let's geometry this guy, because clearly that's a box whose area is 4, and then we can split the integral, so between 1 and 3, and split it between 3 and 6. They gave us this function, this piece of our function, and so we can do a direct calculation of the integral on that. Okay. So 4 plus whatever this integral ends up being. So when they ask us for the integral from 1 to 6 of gx dx, we're going to treat it instead as the sum of the integral between 1 and 3, which we just figured out is 4, and the integral from 3 to 6. Okay, from our geometric interpretation, the first part of this sum is just 4. This guy, we can sub in the piece of g of x that we need, which is 2 times x minus 4 squared dx. And then we're going to have to compute this guy directly. Okay. Technically, we're going to do u sub, though you don't technically have to because the u here doesn't kick anything out when you take the derivative, but just to be as concise as possible, or clear, we will do a quick sub. So if we let u equal x minus 4, then du equals dx. And so really we're looking at the integral and let's pull that 2 out, let's say. Twice the integral from 3 to 6 of u squared du. So this is equal to 4 plus 2 times u cubed divided by 3 from 3 to 6. Sub back in for u. Four plus 2 times x minus 4 divided by 3 3 to 6. And I'm going to start moving to the right here maybe. So we get 4 plus, so we can't quite box this yet, we still have to do some subbing in. 4 plus 2 times 2/3. 6 minus 4 is 2, divided by 3, 2/3, minus 3 minus 4 is -1, so that really turns into plus 1/3. Okay, and you could certainly box this and go, but since we're so close, did I screw this up somehow? Oh, forgot the cubed. Gotta have the cubed in here. My bad. So really this should be 8/3. And this should still just be 1/3. Okay. So you could definitely box this up and move on with your life, so you don't make a silly mistake like adding 8/3 and 1/3 and calling it 7/3, or I don't know, it's the kind of mistake you'd make. But this would turn into 4 plus 2 8/3, and 1/3 is just 3. And so this turns into 10. So it turns out to a pretty nice answer, but definitely ripe for mistakes, like I just showed there. Okay, so the integral is 10. This was a 3-pointer, I believe. You got a point for, let me put this up. You got a point for splitting the integral. Okay, so for recognizing that this would be best approached by splitting into 2. You got a point for finding the correct antiderivative of this part. You got a point for down here. And then you got a point for the correct answer, either here or here. Those 3 points. Okay, so we're 5 points in. 2 parts to go. Okay, so part C asks for the interval between -5 and 6 on what open intervals, let's underline open because that's important, if any, is the graph of f both increasing and concave up. Give a reason for your answer. Okay, so increasing means that the derivative is greater than 0. And then concave up, remember way back to the Wayback Machine, means that the second derivative, so the derivative of the derivative, is positive. Okay. So what that means for us, since we do not have the graph of the second derivative, is we are looking, the first thing we need for sure is the parts of f prime, which for us is also g, the parts of g that are above the x-axis, because that will tell us it's increasing. Anything below the x-axis is a negative derivative, which means we're decreasing. So it's got to be above the x-axis, and it needs to be increasing. So it can't just be above the x-axis, it needs to be above the x-axis and increasing. So for our purposes, definitely not above here or here, so none of these. Here we're not technically above 0, and we're not increasing because we're flatlined. So this appears to be our first section that is positive and increasing. Here we're positive, but we're not increasing. Here we're positive, but we're decreasing. The second derivative is decreasing. And here we are positive and increasing. Okay, so our two intervals, and they say give a reason for your answers. But basically we've got two intervals between 0 and 1 and between 4 and 6, and they said specifically open intervals. So now let's justify this. Hold on, lost my picture. There we go. Okay, so the way we're going to justify this is we can only use the graph of g as our justification. So even though, so I should have said this a little differently. F prime, that's what we're looking for, the second derivative greater than 0, but what that means in regards to f prime is that f prime is increasing. That's the justification we're allowed to use. Okay, that is the justification we're allowed to use. And so the way we're going to say that is the graph of f is both increasing and concave up on the open intervals from 0 to 1 and from 4 to 6. And again, our justification can only include references to f prime, which is g, okay? Because f prime of x, which is equal to g of x, is greater than 0. It's greater than 0 and increasing on those intervals. You would not have gotten the point if you said the second derivative of f was greater than 0, because we have no graph of the second derivative. You have to have reference to the first derivative, to g, which is the graph that we do have. Okay, this was a 2-pointer. You got 1 point for the intervals, 1 point for your reasoning. Okay, so that brings us to 7, which means we've got 1 point or 1 part left and 2 points to go. So part D. Find the x-coordinate of each point of inflection on the graph of f give a reason for your answer. So we're just looking for the x-coordinate. Okay. So a point of inflection is going to be a point where our derivative goes from increasing to decreasing. Okay, from increasing to decreasing, where our concavity changes. Okay, points of inflection are where our concavity changes from either up to down or down to up. And the way that we can tell that from our first derivative is looking at locations where we go from increasing to decreasing or vice versa. Okay, but it has to be from increasing to decreasing or decreasing to increasing, which means it cannot be something like here where we start increasing, but we were not increasing or decreasing at all here. We were staying constant. Okay, if we wanted to picture this, this part of our graph is of our function, because we have a constant rate of change, is a line. When we become this line, it becomes a parabola. So it's gone from a line to a parabola, which that's not a point of inflection. Okay, it has to be a smooth point. It has to be, it just has to be smooth there. Okay, so the only point on this graph where we see a true change from increasing or decreasing, or in our case from decreasing to increasing, is at 4. We can clearly see the derivative is decreasing and then it's increasing. No other point shown here has that change. Okay, so this is our point of inflection. And they want to know, well, they just want the x-coordinate because, of course, we don't know what the y-coordinate is since we don't have f. And again, our justification needs to only reference the derivative because that's what we have in front of us. Okay, we can't pull in, oh, well, the second derivative changes or whatever, it has to reference the first derivative. Okay, so D, we can say the x-coordinate of the point of inflection of f is x equals 4. You get a point for identifying that. And then the second point comes from the justification. And the justification is because the first derivative of f of x, which is of course equal to g of x, changes from decreasing to increasing. From decreasing to increasing at x equals 4. And with that justification, you would pick up your second point. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 for 9. And that was FRQ number 3 from AP Calc AB 2018.